the next speaker is Eswar Muthusamy from the Jawaharlal Nehru Center for Advanced Scientific Research. And yeah, the floor is yours, please.
Thank you, Professor Zhao, for a kind introduction. And this. Okay. Yeah, so I'm Eswar Muthusamy from Jawaharlal Nehru Center for Advanced Scientific Research. And, let me take this opportunity to thank Professor Cheetham and Professor Rao for a kind invitation, and also Dr. Natalia and the organizing team for the wonderful arrangement. It's always very pleasant, exciting to come to IVAM meeting, and this is my third meeting to come here. Today I'll be talking on electrochemical water splitting using this metal phosphates and oxide material. And electrolysis of water to produce a green hydrogen is essential for that future renewable energy. And almost the green hydrogen gets a lot of attention. In fact, enormous interest is generated among the investors, policymakers, and politicians as an what you call, it's a game changer to reduce that net zero targets like that in carbon footprint reduction and all. And a lot of mega projects are coming each year, every places all over the globe, the people are announcing for the production of green hydrogen. And in UAE itself, there are in fact, the UAE is planning to capture that 30% of that market or 25% of that global hydrogen fuel market in the year 2030. And they are going ahead, particularly for the export market. And so many projects they are announcing to go with that green hydrogen production. And also nearly $160 billion they are planning to invest in kind of new projects as well as infrastructure facilities to over the 10 years time. And this is the way, yeah. So this is that even here, sorry. So this one in Russell Cam, they are kind of Austria ASEAN group to develop the $3.3 million green hydrogen plant here. And you can see that it is a fast emerging field in this area. And green hydrogen, when I say, the world over, there are almost 70 million tons of hydrogen produced annually. And more than 70% of this hydrogen is used for ammonia and refining industries. In fact, they consume nearly 20,000 tons of hydrogen per day. And almost all the hydrogen coming from the natural gas, particularly methane, steam reforming of methane is some technology. And that's called the gray hydrogen because it releases a lot of CO2 and it's not captured and goes to the environmental side. Then that one is that blue hydrogen, where the CO2 is captured or stored or converted into a different product. So that we'll call as a blue hydrogen, so labeled as a blue hydrogen. There's a green hydrogen where it's a electricity generated by green process, renewable sources, and then you are getting that hydrogen with the side product oxygen. And if you look at the production cost, to produce the gray hydrogen, it's nearly $1 to $2 per kilogram. Whereas if you go to for green hydrogen, right now it goes to the 2.5 to $6 per kilogram, depending upon the process which you are looking for the generation of electricity. And this one, blue hydrogen, which is coming around $2 to $3 per kg. So there's a lot of scope and a kind of investment in this direction is enormous. And you can see that here, Dubai Electricity and Water Authority, so this is the Middle East's first solar-driven hydrogen electrolysis facility. It's kept in that solar park here in Dubai. And even Abu Dhabi ports to build, they're planning to build some 2 gigawatt green hydrogen projects. So a lot of things are happening. And when you say that the process is same, you have that electrolysis, the water have that chamber where that cathode chamber and anode chamber, where the cathode you will see the hydrogen reduction and anode with that hydrogen, the H plus reduction or water reduction you can say. And here oxygen evolution reaction, hydrogen oxidation, water oxidation. So in acidic condition, you can see that this type of reactions happening. And in alkaline solutions, so in both cases, you see the water splitting, either you know that whether you're in alkaline or acid or neutral, the thermodynamic potential always so 1.23 volt. You have to supply this much energy to split that water. And the membrane is separating. In fact, the industrial process comes with a proton exchange membrane or anion exchange membrane or alkali hydrolysis of water to produce it. In fact, alkali hydrolysis of water is at almost 50 years old technology. And now people are moving towards a kind of membrane-based process. But again, the challenge, if you look at it, if you are going for an acidic medium, is a process you can see is the more what you call feasible, because you will be having a huge number of protons available in acidic pH. But the problem that you have to use that at the corrosive conditions, very costly metal like noble metals type of things. And OER reaction, again, is a very sluggish multi-step reaction. The whole process, depending on the kinetics of that OER reaction to say, because it's a multi-step and complicated process, sluggish reaction, transfer, electron transfer, and other process. But alkaline OER is a bit more faster, but again, you will be living with that less number of protons, and that will reduce the reaction. So there is, in both places, you will see that problems, and then people, each one has own merits and demerits in that way. And you can see that thermodynamic potential, I said, this is a 1.23 volt for that ideal thermodynamic potential. Anything you will be using the catalytic electrocatalysis, where even then you have to apply certain additional potential to make this reaction happen. This is called over potential. So you have to apply over and above, you have to apply the potential over and above the thermodynamic potential that you call the over potential. And you can see that the higher the over potential, the catalyst may not be that effective. But if you have the state-of-the-art catalyst, ruthenium oxide, iridium oxide, people are using it in high pH conditions. Again, the problem with the cost, scarcity, stability in wide pH range, and it's also expensive and non-conductive. So going for that non-expensive metals, particularly the tungsten metal-based electrocatalysts are getting a lot of attention. People use it to metal oxides, tungsten metal oxides or oxymetal hydroxide, chalcogenides, nitrates, and metals and alloys. Various design strategies for oxygen evolution reaction catalysts, people use it. They introduce heteroatom or vacancy or strain or doping, and even creation of interface engineering, phase modification, and various strategies people try to use it to get that higher activity and with a less, reduce the over potential of this material. Oxides has a problem, so particularly conductivity issues, and that kind, the metal phosphates are getting little recent attention for their little over potential reduction, as well as active sites for both hydrogen and OH absorption, and also favorable absorption kinetics and tunable electronic structure with the high electrical conductivity compared to oxide materials. And again, it's low price. And so I'll be touching upon this phosphate, which we used for this one, metal phosphate. Here our strategy based on the synthesis technique, and that iron phosphate, cobalt phosphate, and also the oxides which produced by a borohydride reduction strategy, iron compound. And as I said, that phosphates a lot of attention in recent years. Many people use it, cobalt and iron phosphide and nickel phosphide, and so on and so forth. But in all the cases, they are always having the problem, still the over potential for it to reach that even 10 milliampere per centimeter square current density, you have to live with it more than 200 over potential millivolt. But even if you go for like a little higher, 500 millivolt over potential also, you will be having the current density is very low. Even for an industry level, you have to look at it at least 1 ampere level of current density per 1 ampere per centimeter square the current density to make it anything, to think about anything industrial scale. And also stability is not too high for except 10, 12, 20 hours or 30 hours, you can see that. And the one problem is that they are using the bulk precursor, the low concentration of active sites in the final catalyst. And reaching the high current density is a big issue. And long-term stability at high current density is challenging. So here we wanted to increase the active sites by making the precursor, which is like the high surface area precursor, which is prepared through the borohydride reduction of both cobalt and iron hydroxide. And this strategy, which we used for preparation of metal nanostructures, a kind of gold and other strategy where kinetically controlled nucleation side we use for bringing the porous nanostructures of gold or even silver and other platinum and palladium kind of structure, which we wanted to use it for this kind of iron cobalt structure also. So here what we have done, the same method we have, sorry. Yeah, so, sorry. Yeah, so we have taken the cobalt and iron salt, the simple sodium borohydride reduction to optimize the kinetics of the by concentration and temperature. And then whatever obtained hydroxides of iron and cobalt to make it phosphorization and get it cobalt iron phosphide. So this here we have taken both the salts in the same solution and then followed by the reduction. And our kind of LSV source that you can look at it compared to iron phosphide and cobalt phosphide. And this is for iridium oxide standard control. And this cobalt, this is 1:1 cobalt to iron we have taken. And it shows that very good, almost 680 milliampere per centimeter square at around 1.7 voltage. So eta 10 is still a little high. And then we have looked at the structure, but it is very difficult to identify what phase is forming. We are almost getting the almost similar type of iron oxide, iron phosphate, cobalt phosphate structure. So it's not clear it is a one phase or a different one. And again, we optimized to get that good activity at that ratio of cobalt 0.2 and iron 0.8 in this composition. Then we realized, so if it is an individual phase, then if you make the two phosphates separately and you mix it and grind it and you see whether you have the same activity. In fact, we just make this iron phosphide, so taking iron sulfate, iron precursor and cobalt salt, and then phosphorization, cobalt phosphate and iron phosphide, and just to mix and grinding and look at that activity LSV, you can see that very high, almost like 1.37 ampere current density per centimeter square at eta 10 220 millivolt, huge reduction and a very high enhancement in the activity just by mixing the two phosphide particles separately. So we have looked into that. The best activity comes from that cobalt to iron, so 0.2 to 0.8 ratio. And you can see if you take that completely iron phosphide without having any cobalt, your activity is very, very low current density. Whereas if we introduce a 20% cobalt phosphide into this physical mixing, into the iron phosphide, you have that current density at 1.73 volts, almost like more than 1.3 ampere per centimeter square. So over potential also a huge reduction when you are adding little addition of 20% COP brings down this overpotential for eta 10. And all the studies with characterization which shows that critical interfaces, you can see that the FEP, COP, the mixture of these two, gives that if used nanoparticles or heterostructure in between this particle, we can be seen from the TEM, and even EDAX, that elemental analysis shows that, mapping shows that the presence of iron, cobalt, one over other. And XPS analysis clearly shows that there is the COP bond, the CO2p peak, the shifts happens almost a 0.3 electron volt, whereas in the iron you see that it's a negative shift 0.4 electron volts, shows that there's a charge transfer interaction path between cobalt to that iron, so which could be an interesting to look at it. And the Raman analysis also shows that in addition to that, there are surface oxide, presence of surface oxygen, so corresponding to FeO-CO bonds, peaks are available for that. And to look at that kind of electrochemical active surface area by double layer capacitance, and you can see that compared to that cobalt phosphate and iron phosphide, which is a 6.6 millifarad per centimeter square, so that mixed iron phosphate and cobalt phosphide, which is at 0.2, this is a 0.8 iron and 0.2 weight percentage wise. Cobalt is 20%, I can say, and iron is 80%. So it shows that almost double the time of this FEP double layer capacitance. So that means one way that you can think it can be increasing the number of active sites by mixing these two particles, or it could be, but our normalized to that current density shows that very high. If that just to increase the number of active sites, if you normalize to the current density, it will not be showing any change. But in this case, it's a higher value, indicates that there are that increasing the intrinsic activity of this phosphide by seeing this heterostructure. And Tafel slope, which is a measure of how the current density changes with increasing over potential. And it shows that very good reduction, low value for this FeP-COP mixture. And the mass activity, you can see the very huge increase. If you go from that over potential range at 500 millivolt, you will see that almost like 19,000 ampere per gram convert into that weight scale, iron and cobalt. So at lower over potential, you will see that nearly 1,700 ampere per gram. So it's a huge mass activity as compared to that cobalt phosphide or iron phosphide. At any over potential, you can look at it. So even for impedance analysis, very interesting, it shows that and kind of very low charge transfer. So the low RCT value, particularly for this corresponding to that FeP-COP compared to that other individual phosphides, indicating that fast kinetics associated with this interaction at that heterostructure. And you can also see that you can have that very high stability, almost like a 200 milliampere per centimeter square. You can keep this thing stable at 200 hours, whereas the iridium oxide, which is not stable even for 50 hours in this current density. And at a constant potential, you can see. And it's also almost stable for 300 CV cycles, so indicating the robust activity of this mixture. And even stepwise multi-step pronoamperometry shows that it's versatile to look at it at any current density. You can see that very stable at over a period of a few hours, and you can also bring it to step down approach. And even the looking at this one, you can see to draw that 30 milliampere per centimeter square the current density. So you can even keep this potential constant almost. In fact, with the time 300 hours, the potential is even coming down. So that means still there are structural transformations happening during this process itself. And if you take that in a full cell potential study, it also gives 1.56 volt with a 10 milliampere that current density per centimeter square, and with connected with the FEPCOP as a working electrode with that counter PTC. So we will be able to get that eta 10 milliampere per centimeter square, so 1.56 volt will be sufficient to do that. And what is the species in this process? So since a phosphate will it be stable because electrocatalytic, many of the materials are applying the potential are subject to this transformation. And in fact, many times you'll see that's a pre-catalyst. What is the actual catalyst? We have to wait after a few cycles. In this case, in a phosphate also, we have done such a study where we have seen this, the phosphate when you are treating with it in the conditions for a few cycles, it goes into that, the surface is getting oxidized. It develops hydroxy surface, and then how this transformation happening in alkaline medium. We have looked into that, and after that post-OER analysis, we still find that there are crystallite size which is of the order of 10-20 nanometer, and again the formation of interfaces is still existing, but it's a more little amorphizations also happening, increasing the porosity and so on. Even our XPS study indicates that formation of a metal-oxygen bond in this thing. So indicating that there are almost some 10-20% of that the analysis. We see that oxide surface on the phosphide matrix to say that. And we have with Professor Umesh Wagmare, we have the calculations how this active site, since our analysis shows that post-reaction, the formation of oxy-hydroxide surfaces. So he have created the surface things and created that phosphides. The surface you change with the oxide and hydroxyl groups, and allowing to relaxation to get that structure without much modification. And then look at it that Gibbs free energy intermediate in the each reaction step. What is the energy of Gibbs free energy absorption by attaching that oxygen, OH and OH group at each sites. And then, so this of OH prefers to first absorb on the cobalt, then that iron, though the iron interacts with the cobalt very strong, once absorbed it won't go out, whereas so the first preference, the OH goes to that CO sites, and then that removal of hydrogen from that OH, and then followed by addition OH forms COOH, and this further releases the oxygen. So the energetics, if you look at it, compared to this cobalt phosphide or iron phosphide, this mixed one at the 0-1-1 surface, you'll be seeing that very good, the lowest free energy absorption is very fast moving step in this way kinetically. So that's where compared to any other steps, here the OH to O2 step is very, very low energy here. So favorable for this fast reaction at the interface. And to conclude this, material with the physical mixing, creating that kind of nice heterostructures type of catalyst is very amazing to see here, which shows it efficient heterointerface formation, high current density, almost 3 times higher than what individual phosphides, and high mass activity, and the effective decrease in the Gibbs free energy for oxygenated interface, and even stability for 200 hours at the current density of 200 milliampere centimeter square, and with eta 10 220 millivolt. So it's a very interesting, just a kind of serendipity type of thing, just mixing the two mixer and then create that catalytically active surface. And then next I will just quickly go through a few minutes that creation of, in this kind of HER and OER, the bubble formation, when the gas evolution happens, the bubble formation is a big problem that will be reducing that actual performance of the catalyst. In fact, when the bubble creates, so it blocks the sites, the effective surface sites is occupied, so the void fraction at the electrode surface and electrolyte increases. It also reduces the conductivity of the electrolyte, and therefore you have to give more potential to derive the same current density. So that means the over potential increases. So there are various approaches. People try to go with some magnetic field assisted water splitting, where there are 2-3 mechanisms people allow that. One is indirect way of doing that process, a magneto-hydrodynamic induced convection. By using this Lorentz force, apply the magnetic field, that Lorentz force pushes these bubbles in that way and clean the surface, thereby enhances the activity. It's an indirect way of enhancing the hydrogen, the water splitting. Another one is that magnetothermal, where you can apply the high frequency, alternate high frequency of magnetic field, and then you raise the temperature locally and then enhances the catalytic activity. That is a magnetothermal. So these two are more of indirect one. Another one, recently people are coming up with that field-induced spin selectivity. We say that the nickel going from singlet state, the alternate nickel in the magnetic field goes to that triplet state. So thereby that OH hydroxide getting binding to this in the same spin state. And then when it's going out, the oxygen goes as a triplet state without much energy spending. So there is a very field-induced spin selectivity by inducing the magnetic field. So the favorable spin triplet state for O2 generation is achieved in this kind of material. So we have looked at that kind of a magnetic iron structure, where we found it's a very nice nanostructure which we wanted to check for this type of magnetic field induced reaction, how it performs. And we prepared the same, just a simple borohydride reduction of iron precursor, and get that beautiful nanostructures with the filament-like structures due to this magnetic properties. And if you look at the iron nanostructure, O means in the absence of magnetic field, B is that in presence of magnetic field. We applied a magnetic field around 150 millitesla, just a normal magnet, and you can see that at this around 1.46 volt, you will be seeing that without magnetic field and with the magnetic field, a huge jump, whereas in other cases where the just a nickel foam. So this catalyst, we put it in a nickel foam as your current collector. Iridium oxide, you won't see any big difference here. And also look at it, how much the percentage of magnetocurrent increases. If you look at this 1.67 range, you will be seeing almost in this 1.4 volt, you will see almost 100% increase. You can say that from this state to this state, almost like a very high jump in this current density when you just apply the magnetic field. So you can 100% increase magnetocurrent with the magnetocurrent density of 800 milliampere per centimeter square. And even for the Tafel slope, all shows that your iron nanostructure in presence of magnetic field. So you do the magnetic structure on nickel foam and apply magnetic field for a few cycles, and then you remove the magnetic field, and then still shows that very high enhanced activity and with a very low Tafel slope. And you can also see that this double layer ECSA also shows that a very double time increase, so almost 100% increase in this ECSA, active surface area. So, and you can even derive it at a kind of a potential for 1.7 volt, you will be getting like 1 ampere, and then you can see the 2.76 volt you apply, you will be able to get a 5 ampere current density. And in a higher level, you can reach up to 15 ampere current density. Just like in a calorimeter, you will be able to see that how active they are, linearly it goes. And this is all with the iron structure. We have to apply the magnetic field sometime and recycle it few 100 cycles, and then you will get that active things. Even for HEA reaction, it shows a very good activity when you apply the magnetic field. And stability wise is also amazing performance. And if you look at it, it's at 1 ampere current density per centimeter square. You see it's stable, even no change in potential, it goes like almost 3,000 hours stability in a months-long stability. And even if it go for drop 5 ampere current density, you still see that more than 300 hours is stable. So we are now looking at it. In fact, when you do the reaction and scratch the material and put it in a carbon paper and then do the reaction, and we are not getting, though increase is there, but not getting that activity. So when the analysis of those materials shows that the formation of new phase in nickel and iron is a spinel type of structure, and it's still not clear what is that actual spinel or some other structure is active in this, behind the thing. So you need a nickel foam and add the iron nanostructure. With the reaction, it forms an active interface, forms like a spinel type of interface, and give this high activity. And also this is a control, the same thing which we have done with the control. You won't see in kind of carbon paper this kind of enhancement, though the only in the nickel which will give that very high improvement. So that is, other study shows that the XRD of the used catalyst shows the formation of ferrous iron like a spinel type of things, but still it's not yet clear how the structure which we are still working on that to get it cleared. Okay. So used catalyst after post reactions shows that iron nanostructures, and is all the lot of porous morphology, which is not clear how that nickel is placed in this kind of system. And to conclude, so we have seen that this catalyst is active for both OER and HER, and with a very low overpotential, and gives a very high current density. You can achieve up to 17 ampere per centimeter square, but higher potential. And even for that hydrogen evolution, you will be able to get high current density at potential of 3.3 volt. Stability exceptional, very even 500 milliampere, 1 ampere or 5 ampere, and goes in more than a month stability also. So highly durable. Electrochemical generations, it shows that new heterostructure is forming, and what structure exactly which we have to still work on that. So with this, I like to acknowledge that the student who worked on Divya Putani and the collaborator who is in the audience, Professor Umesh Wagmare, for the calculations, and the student, Dr. Shashank Chaturvedi, and Professor Chandravas for that Raman spectral analysis, and the financial support for JNC and DST. So thank you once again.
Thank you very much. Now the floor is with questions.
Yeah.
Yes. You can walk there. Oh, okay.
Thank you very much for the nice talk. My question is, are you forming a solid solution, or is it really an heterogeneous structure, cobalt, iron?
It's just a solid solution, just mixing these two.
So they mix? Yeah.
Just a mixer, yeah.
Because from the modeling, when you present the modeling, it looks like you have an interface between the cobalt phosphide and the iron phosphide.
So this is each like a kind of individual particle type of thing.
Okay, thank you.
Yeah.
Yes.
Thank you for the presentation. And I have a question in the first part of the talk, mainly about the iron cobalt phosphide.
Which one?
The iron cobalt phosphide. I noticed in the LSV there was some sorts of peak, like merged with the oxygen evolution reaction. So how could you explain this? Is
Which
it
one, in LSV you are telling?
Yeah.
That's a kind of the oxidation potential of those iron and the cobalt, yeah.
So,
oxidation potential. So you will see this type of things because it's not in the multiple oxidation state cobalt can exist. So you will see that depending on the potential you're applying, you will see that small peak.
I mean, at this point, we cannot distinguish the current due to oxidation of the species on the surface
No, you
from
can
the
remove
current
that. It is not overlapping exactly in the same region. So it goes in the early potential. So where you are looking at that current intensity, where it is completely associated with the OER.
So the iron kept oxidized, however, the phosphide cell not oxidized?
Pardon? Iron?
I mean, the phosphide, according to the results, it keeps its form.
Iron.
It does not suffer from any reconstructions.
No. So,
Is it like the post-stability measurements occur after mild process or harsh process? Because to my knowledge, it should like suffer from some sort of oxidation.
yes, yes, that's what it goes to that iron oxide, hydroxides, the surface. It won't be, the phosphate won't be stable all the time. So you will be allowing for longer time. In fact, you will see the more and more the surface is getting oxidized. So if you allow for more than 200 hours or something, you may even have more phosphate rather than,
Okay,
yeah.
thank you.
That's the one problem in that phosphate.
Yeah, I have a last question.
sure.
You showed that this is the mixture of the cobalt, phosphide, and iron. You showed some TEM images. Did you see that they are separated? They grow together, or
Yeah, they're just. Probably you will be the right person to look at it. How that's at the interface. How is that any diffusion of things? Probably to look at it. But they are cobalt, phosphate, and iron phosphate. The interface formation. So
Okay.
to that extent, we are able to see that. Yeah. So how at the interface, how the atomic level we couldn't that facility to see.
okay? So with that, I'd like to thank you again.
Thank you. Thank you.